What is the story of the Copernican Revolution that you're familiar with from, I don't know, school, popular culture, whatever?
That he discovered that the Earth does not revolve around the sun.
Okay. We have these naive ancient peoples who didn't know well enough. They thought the Earth was the center of the universe. We have this heroic figure, Copernicus, who shows us the light, and we adopt the heliocentric view of the solar system that we have today. And aren't we so much more advanced than everyone was back in the past? I want to present a little bit more nuanced view of the Copernican Revolution than that. It is, to some extent, or can be, kind of a case study of how the scientific method works. The way I'm going to be presenting it, though, is very much more idealized than what real life was like for the people involved. Okay. First thing I want to stress is there are damn good reasons for thinking that the Earth is the center of the solar system. Enel. Why? I'm this rabble-rouser who wants to tell you that contrary to what you and your forefathers have believed forever, that the sun is actually at the center of the universe. Tell me why I'm wrong. You can draw on some lifelines if you want. What is the evidence that the Earth is at the center of the solar system?
As you look up to the sky,
I look up, things up there are moving. Right? Heavens are moving. And conversely,
Yeah,
I'm not. I mean, do you feel the Earth going around the sun? Okay, the Earth seems to be stationary. Yeah.
Seasons.
Seasons. What about seasons? How do the seasons?
Well, the reason that season exists is because it's still towards the sun. So, if the sun is revolving around the Earth, then it would be a constant all year round.
Okay, so you're actually thinking that seasonality argues against the idea that the Earth is at the center.
Yeah.
Okay. Right now I want arguments that we can propose that the Earth is at the center of the solar system. If the Earth were moving around, not only should we feel that the Earth is moving, I mean, if you're on a wagon and the wagon is moving, what's your experience? If you feel the wagon moving, what else do you feel? This is the wagon. This is open to the air. Horses are galloping along. What do you feel? You feel the wind. Okay. Well, if the Earth is moving around the sun, why is there no kind of wind, or why aren't we? Why isn't it obviously that we're moving through something? It's pretty clear that our moon is revolving around the Earth. If we're revolving around the sun, why doesn't our moon fall off? Right? Okay. So the main point I'm trying to get across here is that the geocentric view that the Earth is at the center of the solar system is not unreasonable. It matches up with our common everyday experience. So I'll just leave it at that. We'll come back to this point. Not unreasonable. Okay, so this should be familiar given the readings you did, but here is the geocentric or Ptolemaic model. Earth at the center. I got this from, I don't know, I think some Polish site. So the names are in not in English, but going out from the Earth at the center, We have the moon. And we know that the moon is further out than the clouds. Well, how do we know that?
Because the clouds can cover it.
Clouds can cover it. Clouds can pass in front of the moon. Okay? We never see clouds go behind the moon. Okay? So we've got this level of atmosphere. And then clearly the moon is above that. And then in this geocentric view, we have a couple of planets, Mercury and Venus, that come next. And there's and the sun beyond them, all going around the Earth. And there's something a little strange about Mercury and Venus because they're never seen very far in the heavens away from the sun. Okay? You'd think that with these circles, why couldn't the sun be over here and Mercury be over here? But just observationally, we see that Mercury is never very far away from the sun at all. The only times we can see Mercury is shortly after sunset or shortly before sunrise, very low on the horizon. And then, as the sun sets further, Mercury disappears with it. Same thing with Venus. Venus has a little bit more latitude. It can get a little bit further away from the sun, but it's always, in the same direction as the sun. So that makes those two planets a little bit different. And then going further out from beyond the sun, there is Mars and Jupiter and Saturn. And during the Ptolemaic time, those were the planets. No Uranus, no Neptune, no Ceres, no Pluto, no Sedna, none of those. Okay. So, this geocentric model can explain the movements. It's built to explain the fact that the stars, which are these fixed stars, are in this outer sphere beyond, and the wandering stars, the planets, and the sun was considered a kind of wandering star as well. All are moving around the Earth, and that explains the fact that night after night we see the stars moving in a certain direction, and we see the planets moving against the stars and so forth. Heliocentric, not sure I need to say much about this because you all grown up with this since kindergarten and before. Okay, sun at the center, Mercury, Venus, Earth, Mars, Jupiter, Saturn, with the moon going around the Earth. Just a quick digression. The reason why this topic of Copernican Revolution is so interesting for a Mars class is that Mars played a key role in the changing of this cosmology, our perceptions of the cosmos from a geocentric to heliocentric, because of this retrograde motion issue. Again, if we go out early morning these days, we'll see Mars low on the horizon against a certain set of stars. If we look the next day, it's going to be a little bit further to the east. So it's going to be traveling from west to east, and then eventually it will back up and go through this retrograde motion. So this is very curious. Saturn, if you look real closely, Saturn does this as well as does Jupiter, but it's really this bizarre behavior on the part of Mars that got people wondering what's going on. Now, in the geocentric model, they introduced these epicycles to explain these retrograde motions. I don't know, how many of you have played with spirographs? Okay, if you've got these wheels going around in wheels, that you get these looping kind of motions. And so that's really what epicycles were meant to do in the geocentric model. And over time, the geocentric model kept getting more and more complex in terms of the number of cycles and the displacement of the Earth from these different cycles in order to do an increasingly good job of explaining where the planets were going to be. Retrograde motion is explained by heliocentric model in this other race car format that I just talked about earlier. Earth is speeding by on the inner lane, Mars is on the outer lane. As Earth is catching up to Mars, looking past Mars towards the stars that are outside of our solar system, we see that Mars is trending, in the prograde direction. But because Earth is going faster, when Earth passes Mars, and we look from Earth back to Mars, it's going to look like Mars is showing up against stars that it had passed a little bit ago. Go through this retrograde motion before coming back around to this prograde motion. So what I want to do here, just very briefly, is compare these two models. Ideally in the way science ideally works is you create multiple hypotheses about how the world works, and you make empirical observations to throw out some models and keep others. And it's by discarding and falsifying models that don't work, we can leave them behind and we can focus more and more on the models that do work. Does the geocentric model explain the movement of stars and planets across the sky? That's what it's built for. So yes. Okay. This is not time to dump on the geocentric model. Okay. Heliocentric model. Does it explain movement of planets and stars? Yes. Does the geocentric model have a way to explain this bizarre behavior of Mars, this retrograde motion? What is it? Epicycles. So yes, epicycles. Does a heliocentric model have a way to explain Mars's retrograde motion? Yes. The relative orbital velocities. Can you use the geocentric model to predict where the planets will be? Yes. Can you use the heliocentric model to predict where planets will be? Yes. Is there a mechanism on explaining how this works for the geocentric model? Well, yeah, there's, it's nothing that we've got direct experience with, but there are these celestial spheres, and the planets are on these spheres, and the spheres are moving around, and that is causing the planets that we see to move across. And the heliocentric model, does that have a mechanism? Yes, although it took a while to get to it. Clearly everything is going around the sun, so there must be something about the sun that is driving the motions of the planets. Okay? So both of the models explain what the models were meant to explain. They both account for Mars's retrograde motion. They can both be used to predict where planets will be in the future. They both have kind of a mechanism associated with them. What makes one model better than the other at this point?
One of them is true and one of them isn't.
Okay. The question then becomes, if you've got these two models that both explain what's going on, how do we eventually throw out one of them and keep the other? What if we make more and more observations?
I was just going to say that would include building a telescope.
Well, clearly we're talking about pre-telescope days here, but just having a telescope by itself, if all we're doing with the telescope is getting more and more accurate positions of stars, we're not going to be able to distinguish between these two. Well, the point I'm trying to make here is that at some point you need to come up with, well, let's push these models by applying them to something else and make them make predictions about that something else that we can maybe distinguish between the two. And the something else is going to be the phases of Venus. So I want to just spend a quick time here talking about what we mean by planetary or lunar phases. So sometimes we see a full moon, right? Other times we see a quarter moon. Sometimes we see a new moon where most of the disk of the moon is dark. What does that actually reflect? What?
I was going to say the shadows of the earth.
It's actually not the shadows of the Earth. A lunar eclipse would be the shadow of the Earth on the moon. At any one time, about half of the moon's surface is lit up and the other half is not. And why is that? Sunlight, okay. Half of the moon is going to be pointed in the direction of the sun. Half the moon is going to be pointed away. The half that is pointed toward the sun is going to be lit up. And it is how that half of the sun that is lit up, how that is pointing toward us, that determines whether we see what phase of the moon we see. So when we have a full moon, the moon is not quite exactly behind the Earth. Probably either above or below. Otherwise, we'd have a lunar eclipse. The sunlight is coming in, shining on this side of the sun, of the moon, and that is the side that is pointed toward the Earth. So the whole half of the moon that we can see is lit up, and so we call that a full moon. As the moon moves around in its orbit, let's say it comes over here, what kind of a view are we going to see? Of the half of the moon that we can see, half of that half is pointed toward the sun, and half of the half is pointed away from the sun. So we're going to see up in the sky, the moon is going to be half lit up and half dark. Okay? So that's basically all that's going on with the phases of the moon. But anybody that is getting illuminated by the sun that can be viewed from some other location in space can also exhibit phases. Okay. So what we're going to do is take these two models that both predict how planets move around the solar system, and we're going to see, do they vary in terms of what they predict about the phases of Venus. And your reading actually talked very briefly about Galileo using his telescope. So someone was mentioning the development of the telescope to look at Venus and look at the phases of Venus, but didn't make much of it. And I want to make a little bit more of it. So, in the geocentric model, who is at the center of the solar system? Geocentric? Earth. Okay. So if we've got the Earth here, and we have the sun going around in an orbit, and somewhere in between is going to be Venus. And Venus goes around in this little epicycle between the Earth and the sun. And so at some point, if this is the orbit of Venus, and it is going around on this epicycle around that, at some point in time, Venus could be here. And at other points in time, it could be over here, and at other points in time, it's going to be over here. So I wanted you to take the paper that I handed you out. And pretend you are standing on the surface of the Earth, looking at Venus with the sun out beyond. And you can see Venus here at time 1, here at time 2, and here at time 3. And if you observe Venus, what would you see? What would your basic data be? It's going to be a dot in the sky, right? is that dot going to look bigger at time 1 or at time 3? Time 1. Okay. So one thing you can notice about planets like Venus is their relative size. Okay. So if you looked at Venus at time 1 and drew a circle to represent the planet, and then looked at Venus at time 2, would that circle that you draw be bigger or smaller? Smaller. In time 3, smaller still. Okay. So on your paper, draw a circle for time 1, a slightly smaller circle for time 2, a slightly smaller circle for time 3. Now, the sun is at the top there, the Earth is at the bottom, Venus is in the middle, going around in circles. On top of those big, smaller circles, what do you expect to see in terms of the phase of Venus? How much of what you can see of Venus at this point is going to be lit up, and how much is going to be dark? Draw. Same thing here. How much is going to be lit up based on where the sunlight is coming, which part of Venus is lit up, how you're looking at Venus from the Earth. The same thing here. Here you're going to have your smaller disk of Venus based on where the sunlight is coming and how you're looking at Venus from the Earth. How much of Venus is going to be lit up and how much is going to be dark? Let's try it again with the heliocentric model. In this case, we've got sun in the center. We have the Earth going around on a big circle, and Venus going around on a small circle. And let's just keep the Earth in one place here. And again, we could see Venus in different parts of its orbit around the sun compared to where we are. Of course, we're moving, Venus is moving, but at some points in Venus's orbit around the sun, it's going to be in this kind of a relationship between the sun and the Earth. Other times it's going to be over here. And other times over here. Again, when you are observing Venus at this part of its orbit, over here, it's going to look relatively large or small? Large. Over here, smaller. Back here, when it's behind the sun, smallest of all. Okay. What are we going to see in terms of phases of Venus when it is in this position here? Actually, let's just talk this out. Half of Venus is going to be dark, right? And it's going to be the part that is away from the sun, right? So if we are looking at Venus from here, what are we going to see? Mostly dark. Okay. So at this point, Venus is going to be large or small? Large? Mostly dark or mostly light? Okay. So, large and crescent shaped. Venus is now over here. The half that's away from the sun is dark. When we are looking from the Earth, is Venus going to be large or small or in between? Okay, in between. Is it what kind of a phase is it going to be? A new Venus, a full Venus, quarter Venus? Quarter Venus. Okay. So this one is going to look like a relatively large crescent shape with the rest of Venus in the dark, except it would be the other side. Here it's going to be smaller and half. And what about over here? It's going to be very small, and if we look, the side of Venus we're looking at, is it going to be mostly lit up or mostly dark? What? From Earth.
Mostly light.
Mostly light. So we would see a kind of smallish Venus, but most of it would be light. There'd just be a little bit of dark. So, what do we see? Here are pictures of Venus from Hubble. So these are much better pictures of Venus than than Galileo would have been able to get from his primitive little telescope here. But what do you see with the phases of Venus over time? Go ahead.
Well, it's like more mid.
So up here, there's more dark. Is that what you're mostly dark new phase here?
It looks like it goes from large and dark to small and bright.
Okay. So is that consistent with the geocentric model of what you drew? Probably you didn't get very far with the drawings there. The point is that if we go back to the geocentric model, which we'll do in a minute, it would never predict these kind of pattern of phases of Venus. Heliocentric does. So, actually, if science had worked the way the scientific method normally is talked about, as soon as Galileo made his observations of the phases of Venus, it would have been clear that, no, the geocentric model doesn't work. We need to throw it out, and we should adopt the heliocentric model. This, gives you a little bit better view here. So, again, with the geocentric model, with Venus going around its little epicycle here between the Earth and the Sun, mostly what we see is either a fairly dark Venus, whether it's close to us. We either see large and dark, small and dark, or medium-sized and quarter moon Venus, which is not what we see when we look at Venus through like the Hubble telescope. Whereas for the heliocentric model, we either see large and crescent-shaped, somewhat intermediate-sized and half-moon Venus, or small and mostly full-moon Venus, which is precisely what we see for the phases of Venus. So that one new piece of information that is not trying to track the position of planets in the sky or explain retrograde motion or anything, that application of the models to a new phenomenon basically allows us to unequivocally choose between the two. That the geocentric model doesn't work. It makes predictions about the phases of Venus that are not seen when we look at the phases of Venus, whereas the heliocentric model does. So that ideally is how science works. We've got two valid models. They're competing. We apply them to something else. We make new predictions, and those new predictions allow us to throw out one that doesn't work anymore. Just quickly, there were some other things that were going on at the same time. Galileo also looked at Jupiter and saw these moons traveling around Jupiter, which let people think, oh well, you know, if Jupiter has some way of hanging on to its moons as it's going around the sun, then clearly it's not a problem for us to hang on to our moon. Our moon is not going to fall off if the Earth is moving around the sun. Galileo also saw phases of Mars. Mars can never be crescent-shaped with the heliocentric view of the universe because Mars is further away from the sun than the Earth is. So it's never going to be in that period, in that space in between the sun and the Earth that would lead to a crescent-shaped view. Okay, so ideally, as soon as Galileo made those observations, everyone would have said, aha, well, clearly what we have been following for the last 1,500 years, this geocentric model is wrong. Aren't we glad that we can switch over to the heliocentric model because we now know that that's right? Clearly that's not what happened. It took decades for people to gradually adopt the heliocentric model for a variety of reasons. First of all, the heliocentric model that was initially developed was not as good at predicting where the planets were going to be. It was less accurate. If you're going to be making horoscopes, you'd be better off to use the discredited Ptolemaic model because you'd be able to better predict where Venus was going to be, ascending in whatever constellation. A lot is made of the cultural and religious pushback, and clearly that was part of it. The Catholic Church had hitched its wagon to Earth being at the center of the universe, and it was very threatening when it was discussed that the Earth wasn't at the center of the universe. But the religious traditions adapted over time, and are perfectly happy with Earth not being at the center of the solar universe anymore. So that all eventually shook out. But to some extent, it was more a matter of old people with geocentric views of the universe dying off, and heliocentric model of the universe being adopted by the younger scholars coming up. That's always a big part of these major revolutions. You got to wait for us old farts to die off before you can get a new view.